Hello class. This is the class looking at the reactions of functional groups and esters. This is chapter 10.3 and 10.4 of the Heinemann Chemistry textbook. And if you're wondering where we're up to, we're in Unit 3, Area of Study 2, and this whole chapter is about looking at organic molecules. Let's get started. First thing I would like you to do is, in your books, or on a piece of paper, describe a quick technique that can test for the saturation or unsaturation of an organic molecule. That's a quick technique that can test for saturation or unsaturation of an organic molecule. We learned about it last class. Pause the video, write down your answer, and then we'll discuss it. Okay, you found your answer? If you haven't, press pause because I'm going to show you the answer in 3, 2, 1. Alright. If you have a unsaturated organic molecule, for example, like this ethene molecule here, you can expose it to bromine gas being Br2, and it can test for unsaturation by reacting with that double bond and changing its color. So you can, as a visual test for many organic compounds, if you want to see whether it has double bonds or triple bonds, just react with bromine. Bromine is red, but when it's exposed to carbon double bonds, it can be part of an addition reaction, leading to the disappearance of bromine red in the sample. And if you want to have a look at that, have a look at 10.4. Well done. So like I said, we're going to be looking at these functional groups that we looked at last class, the functional groups of organic molecules, but more importantly, how do they react? It's great that chloromethane has chlorine on it, but what's the point? The point of it is that with these organic molecules, you can react them further to make things that you want, or things that we need. And so we're going to be looking at how one functional group's homologous series of a organic molecule, like a chloroalkane, can react into something else. The example here is chloromethane reacting to become methanol. And you can see how small changes of functional groups, or big changes of functional groups, lead to different molecules that you may encounter in everyday life. So the learning intentions today are that you will be able to describe the various alkanes and their functional groups and how they react in specific ways. You will also be able to describe the structure and the characteristics of esters. Esters is towards the end, it's 10.4, and it's very important for the culmination of reactions in organic chemicals. So the success criteria, if you can describe the main types of reactions that these organic molecules can undergo, I'll be really happy. In particular, looking at chloroalkanes, alkanols, and carboxylic acids. And if you can describe how an esterification reaction works, which you may not be able to do yet, that's also showing that you're on a good path in terms of the study design for VCE Chemistry. So the tips that we talked about last class, make sure you have your Heinemann textbook open on another tab, or have the physical book open and as you listen and watch. Make sure you write down the learning intention and success criteria, and make sure that you can actually do it. If you can't do it, or you find that this class hasn't enabled you to do that, make sure you go back to the book and figure it out. If the book can't help you achieve the success criteria, please do number 4, which is to ask questions on Enmodo. Ask them to me, ask them to your classmates, so that we can figure out a way to make sure that you can achieve the success criteria or change it. We don't want to be teaching you things that you don't need to know. We want to be able to set high standards, and I believe that these success criteria are relatively high standards. Make sure that you also write down summary notes. It's great to watch a YouTube video and to learn something new, but when it comes to the exam, you can't take these videos in with you. So make sure that you write down some summary notes. Please don't copy the slides down word for word. Make sure you actually DIY your notes. So let's have a look at these functional groups. The functional groups for these organic molecules, and they're part of alkanes and alkenes. They react in different ways. We're going to look at how the functional groups allow for further reactions and the production of different important organic molecules. So today, in this class, we're going to be looking at 4 different reactions in order. So the first kind of reaction is the chloroalkanes, as we saw on the previous 2 slides on the title slide, like chloromethane. How does it react and what does it react to? reactions of alkanols. So if a alkane or if an alkane has an alcohol group and it's an alkanol, what does it react towards? Carboxylic acids, what do they react towards? And what happens when you put in the carboxylic acid and an alkanol, not an alcohol, they're both the same thing. What happens if you put them together and they form esters? There's some terms that you may come across in this class that you may have to, you should understand relatively well. These are electronegativity, catalysts, primary and secondary alkanols, weak and strong acids, and condensation. These are terms that scientific terms that we use for these reactions, or part of it at least, and so it's good to know what they're referring to. So let's begin. Number one, chloroalkanes are the first one we're looking at because they're the most basic after alkanes. After alkanes, you can do a substitution with chlorine gas and form chloro something. So, for example, here we have chloromethane. And chloromethane can be reacted to create an alcohol or an alkanol. So chloromethane can be reacted to form methanol. And the reason for this is the same reason why chloromethane actually becomes chloromethane from methane. So methane is CH4 and chloromethane is with the chlorine group here. The reason why the chloro group substitutes on one of the hydrogens is because chlorine has a higher electronegativity than hydrogen. And so the higher electronegativity pushes off one of the hydrogens and then it rebonds onto there. OH, the hydroxyl group here, can be in the form of water. And you can see the OH actually displaces the chlorine ion here. The hydroxyl group here has a higher electronegativity, and so it pushes off the chlorine and then joins on to the carbon here to make methanol. So remember, these are all that electronegativity, so you can find this on the periodic table in the back of your book, and also in the data booklet, I believe, as well. So the more electronegative something is, it'll push out something that is less than electronegative. And it's a substitution reaction. Remember, you swap one for the other. Remember our football or netball teams? Swap one for the other. My apologies. Scroll doesn't. So when you have a substitution reaction, if you're reacting with a hydroxyl group, chloro something will react to form an alkanol. So if you have chloromethane and you react with OH minus, or the hydroxyl group, it will form an alkanol. If this was an NH3 group, an ammonia ion, or ammonia atom, or molecule, it forms an amine. You can pronounce it amine if you want, but it is technically an amine. So the NH3 group would actually, as you would expect, NH2 plus would attach, my mouse has disappeared, somewhere along there. And they're the main two types of reaction that chloroalkanes can undergo. It's a substitution, and if it's with a hydroxyl group, it'll form an alkanol or an alcohol. And if it's with an amine group, it'll form a amine. Please note that in your book, when you're reacting chloroethane, it doesn't naturally react with the hydroxyl group. You need a catalyst. So some reactions require a catalyst to overcome, and this is your responsibility to find out which ones do, which ones don't. The questions will help you out from the book. So number two, if we're looking at alkanols or alcohols, we've progressed from a chloromethane to a methanol. Methanol then can react with something else, or ethanol for that matter. Now, when you go from chloromethane to methanol, you make a slightly polar substance into an extremely polar substance, a highly polar substance, which means that it can dissolve in water because like dissolves like, water's polar. Alcohols are polar and they'll dissolve as well. So there's two types of reactions that we want to look at for alkanols, and one's a substitution and one is an oxidation. So substitution here is substitution with ammonia, and you can see here that the ethanol, there's the OH group making an alcohol, an alkanol group, ethanol, and the ammonia in the presence of alumina and at a temperature of 400 degrees Celsius gives you CH3CH2NH2 gas and water. Okay. Now the product is called ethyl amine, and it requires aluminum as a catalyst. So alcohols can undergo a substitution with ammonia and form an alkyl amine, an alkanol or alkane amine. That's reaction 1. Reaction 2 is where you have an alkanol, and you oxidize it. So you oxidize it to carboxylic acid. That should be a 1. So we have ethanol in the presence of oxygen makes CH3COH. Carboxylic acids have, that is the functional group for carboxylic acid, COOH. So ethanol can form ethanoic acid, otherwise known as vinegar. This happens when ethanol goes rancid or yuck in wines, and it reacts with oxygen. So if you have a bottle of red wine and you leave it out for ages, it actually makes ethanoic acid, and that's vinegar. And it makes it taste really, really yuck. Even if you're not a wine drinker, don't drink overexposed wine that's been open for more than a couple of days. It'll taste really, really yuck. In industry, we like to change ethanol into ethanoic acid. But this process here can take a bit of time or require some bacteria to change ethanol to ethanoic acid just using oxygen. It's very passive. So the quick version, and we like quick things done quickly, is to accelerate it using stronger oxidants. Remember oxidation? So if you have a stronger oxidant or oxidizing agent that oxidizes the species quicker or stronger and therefore quicker, that's better for business. So if you put ethanol in the presence of permanganate, manganese, that'd be KMnO4. That's a full molecule. So potassium permanganate or potassium dichromate, those are really strong oxidants, and they will help convert ethanol into ethanoic acid a lot quicker with a couple of H pluses added to the mix. Okay, so it has to be the H plus. If you remember acid and bases, if you see H pluses, think of acids. So in an acidic environment, ethanol can be converted to ethanoic acid a lot easier and a lot quicker. What I want you to do now is pause the video and prove that alkanols to carboxylic acids is an oxidation reaction. So prove to me and prove to yourself that ethanol changed into ethanoic acid is actually an oxidation. We did this last class. How would you prove it? Okay. If you haven't done it yet, press pause and prove that alkanols to carboxylic acid is an oxidation reaction. Otherwise, press play and keep moving on. Now, when we talk about reactions with alkanols, we're still on point number 2, looking at how alkanols react and form carboxylic acids, the COOH group there. It's important to note that just because it has an OH group attached doesn't mean it's automatically going to form a carboxylic acid. And the reason is because the position of the OH is crucial. Okay. Now, this is where those literacy terms of primary and secondary come into play. Alcohols or alkanols are either primary, secondary, or tertiary. Okay, and if you have a look at 10.15 of your textbook, it shows you there. Primary alkanols is where the OH group, your alcohol group, is located at the end of a carbon chain or carbon side chain. These are the ones that can undergo oxidation. So have a look at 10.15 down here. A is meth-F-pro-bute. It is butanol. Okay? Butanol has the OH here on the end of the chain, and therefore it is a primary alkanol. Now, B over here is the same thing. It's butanol, but it's a different isomer, and the OH group is not attached on the end of the side chain, and therefore it is a secondary alkanol. So primary alkanols are the ones where the OH is on the ends, and they will undergo that oxidation to carboxylic acid. Secondary alkanols and tertiary alkanols, which is where the OH is attached even further, like in the middle of a chain, off a chain, it's off the chain, is a tertiary alcohol. But the main important part is not whether distinguishing between secondary and tertiary, but distinguishing between primary, where the alcohol groups at the end, and secondary tertiary. So in the book there's no rules given for how you name a secondary or tertiary alkanol, but just remember that primary alkanols, the one where the OH is on the end of a chain, and not in the middle or not off the branch, are the ones that will actually be oxidized like so. Secondaries and tertiaries will not be oxidized. Okay, we've looked at chloroalkanes, and the chloroalkanes react to form alkanols. Alkanols then react to form carboxylic acids, and this is where we get to number 3. Carboxylic acids, what can we do with them? Well, we know that they naturally react as a weak acid. Like I said before, ethanoic acid is also known as vinegar, and it's a very weak acid. It makes for very good flavoring to put on your fish and chips, and it makes wines taste bad or go rancid. So ethanoic acid is a very weak acid. In the book it describes ethanoic acid as, out of all the ethanoic acids, Ch10.3-10.4 in a bottle, only 1% of the molecules actually ionize to release that H+ to make the substance acidic. So it's a very weak acid, unlike hydrochloric acid or sulfuric acid, which sort of donate their protons or the H+ really, really easily. So carboxylic acids, it could seem like a dead end, but they are really important, because carboxylic acids are the ones that form esters. So if you have a look at this one here, Ch3COH, and this is its ionization to become an acid. Remember, acids donate H+, and so that one there has donated to make H2O+. Carboxylic acids are important because they react with the alkanols. The alkanols are things that we were talking about previously, these ones here. So this and this together, providing you have the right conditions, will actually form esters. And what are esters, other than the name of a person? Esters are what we have here. And in your book, in chapter 10.4, esters are described as chemicals that are particular esters are really important for flavors and smells. So when we have a look at the previous slide, let's have a look. This slide here, flavored bananas. Now, when they make flavored bananas, they don't actually mash up bananas and then lace them on top of the marshmallow thing that's underneath it to make the banana taste. They just make a certain type of ester, and that has the exact same flavors and smells as bananas. It's identical to the stuff in bananas, but you can actually make it in other ways. And we're going to look at that next class. But bananas, or flavored bananas at least, are different in that way where they are made, the flavors are made based on these esters. So esters are here, and the process of making an ester from a carboxylic acid, see the carboxylic acid here, and an alcohol, the OH group there, is called esterification. Terrific, you may say. It's called esterification. It's a very funny name, and that's okay, we like that, but that's what it's called. So here we have ethanoic acid and ethanol. Ethanoic acid and ethanol, the OH groups here, the OH group part of ethanol and the OH group as part of the carboxylic acid arm, react, and in the presence of H+, think acid, so in an acidic environment with lots of H+ around, and with a catalyst involved, we see the joining of two to become one. It is a marriage. And so we have here what was on the left-hand side, which was the ethanoic acid, joins to the O group of the ethanol over here. And the product, you can see here, one of those and two of those, so two H's and an O from here somewhere, actually condenses out to leave out water. So whenever you make an ester, you also produce water. And this is the example we have here. Ethanoic acid plus methanol gives you ethyl ethanoate plus water. And the functional group for esters is RCOO R dash. Okay? So R refers to the hydrocarbon side chain here, and the R dash is the hydrocarbon side chain here. And that is how we describe it. Note that you can't just have ROOR. That's incorrect. The functional group has to have the carbon there. Like I said before, it's a condensation reaction because it condenses water out of the reaction. Hydrolysis is where you add water to break a bond. Condensation is where, just like when you're having a shower and the mirror fogs up or steams up, when water is condensed and is isolated, that is a condensation reaction. Now, an important part of esters is to name them properly, and the chem fact here from 10.4 is a good hint for that. I'll just read it for you. Although the first part of an ester's name is derived from the alkanol, this bit here, from which it's formed, when we are writing the formula, the alkanol section is normally placed second. Okay? Have a look at this. Methyl ethanoate. We name the first part, the methyl group, is the one that is the alcohol group here. Is the methyl group here, but it's at the front of the name. Front of the name and the end of the molecule. Methyl ethanoate. Propyl methanoate. It's hard to tell what they are, but it's important to know which ones they are, because if you had ethyl methanoate, it's actually different to methyl ethanoate. And that's because this COO is not identical on both sides. COO and the O oxygen here is not oxygen over there. So it's not a matter of symmetry, and you could name it either way. But the side where the oxygen is the side that is your side chain. So this one here is ethyl ethanoate. Ethyl is the one on the oxygen side. Ethyl ethanoate. The questions from 10.4, which I'm about to get you to do, are important in doing. So make sure you do them so that you can practice naming these esters. So summary, esters are when you have carboxylic acid and you have an alcohol mixing together and you form an ester link between them, and water is condensed out of it. They have a funny naming system, and this process is called esterification. Alright, we're almost at the end of this class, and so here's what I'd like you to do. Number one, get a piece of paper out, maybe use your textbook, your exercise book, maybe make it A4, and what I want you to do is I want you to draw a flow chart or a flow map showing the pathways that we've looked at from 10.1 to 10.4. Start with an alkane, maybe start with ethane, and ethene perhaps as well, and show how all of them link. How do you get from ethane to chloroethane, from chloroethane to ethanol, from ethanol to ethanoic acid, from ethanoic acid to ethyl ethanoate, for example. Draw a flowchart. Make sure you use it using branches and arrows. Make sure you write down the type of reaction that is taking place, and go through your book and just be clear about what kind of catalysts or conditions are required. Does it require you to have an acidic condition? Does it require you to have a catalyst? What does it require? If it doesn't require anything, don't write anything. But if it sometimes requires things, write it down. Once you've done that, take a picture with your smart device, or scan it if you have a scanner at home, and upload it to Edmodo. And what I'd like you to do is I would like you to upload it to Edmodo, and then I want you to look at other people's uploads and see what they've done, and write a comment. If you think that someone's missed something, you might want to comment underneath it. If you'd like to compliment someone and say, wow, your work is amazing, please do that as well. Make sure you upload your flow diagram, and make sure that you comment on at least one other person's flow diagram that's up there. Once you've done that, work on the questions from 10.3 and 10.4 as per the student guide. Okay, so we've been looking at the reactions of functional groups and esters, and today you should have been able to write down the main types of reactions that chloroalkanes, alkanols, and carboxylic acids can undergo. and you should be able to describe an esterification reaction.